Hello, so today we are doing this problem that asks us to count the number of connected components in a graph. So let's say, for example, we have this graph here, which has these two components. 3, 4 is one component and 0, 1, 2 is one component, so we should return 2 as the result, right? And so this basically means connected components is all the nodes in a graph that are connected together. And so for this one also the output is 1. And so we want to solve this problem. So this here, we can solve this in a different of ways. So we can solve it with DFS, we can solve it with basically DFS is depth first search, with BFS, which is breadth first search. We can also use union find. But today I want to just show how to solve it with DFS and BFS. And so let's say the way our input is structured is that we get the number of nodes or vertices in the graph, and then we get a list of edges. So for example, for this one, we get that there are 5, which are 0, 1, 2, 3, 4. And then we have the edge from 0 to 1, we have the edge from 1 to 2, and then we have the edge from 3 to 4. And our goal is basically to, from this input, to return how many components are there. And so what we can do is basically do DFS and start from any node, and then do DFS basically by traversing the entire thing and marking everything we visited, everything we passed by as visited, and then going to all other nodes that have not been visited yet. And so basically, let me code it up. And so the first thing we are going to do is using DFS. So using DFS. Okay, so that'll be something like, okay. So let's see how can we do that. So the first thing we need to do is, we know that if we have n is like 1 or 0, then there is no need to check. It's just, we can just return n, because that's the number of components. If there are 0 nodes, we have 0 components. If there is just one node, we have just one component. The second thing we need to do is that this list is not really good for the graph. For our graph, we want like one node and then have just all the things connected to it, so that if we have, for example, the node 2 here, we want to say all the nodes that it's connected to, like 1 and 3. This graph, by the way, is undirected. And so we need to parse this list to make this easier, because that will simplify our DFS, because that way we can just get a node and just look directly at the map and find its neighbors. And so let's construct that first. So let's call this adjacency list. So that's the adjacency list like this. And so we are going to construct it as just a map, right? And for each node, let's just say it's a list. So it's a map of keys to values that are lists. So this basically says that if the value is not in the map and we add something to it, it will be initialized to list first. And so we just can go through all the nodes, which are just the values from 0 to n-1. And so in range of n. And basically, we can actually, instead of doing this, we can just go through the list of edges instead. So for the edges we have, so let's say this is start to destination in edges. So this will give me the value in each one of them. And basically this means that for S, it has a destination to be D, right? And so this would be, this is undirected graph. Also D would have, let's just call these U and P to make this clear. So that means that U has, so for example, for 2 here, it has in its adjacency list as a neighbor 3. And 3 also has as a neighbor 2, because this is an undirected graph. And so we need V here to add U. Now the next step is to do our DFS, but for our DFS we are going to have a visited set so that we don't visit a node multiple times. And then what we are going to do is just go through all the nodes, and we are going to check if the node is not visited. We are going to do DFS on it. Basically, say for example, once we traverse this entire 0, 1, 2, we will go to 3, we will find that it's not visited, and then we will go visit 3, 4 to get another component. But we won't visit 1 again because it was already visited when we started exploring 0. And so we are going to say if I not in visited, then what we are going to do is we are going to add it first to visited. Actually, let's just do DFS and let DFS add it to the visited list. And so and we need to pass visited, and also we need the count that will return the number of components. And so we need to increase that, because every time we go here, that means that we are starting a new node at a new node that wasn't traversed by the DFS before. And so let's define our DFS method here. And so what will happen is that whenever we visit something with DFS, we are going to add it to the visited list. And we are going to check basically in the adjacency list here. So we are going to, let's call this node V actually. And then we are going to go to the neighbors of V and traverse them with our DFS. That's what DFS does. So for, let's call this neighbor in edges. Actually, since we constructed the map, the adjacency list, let's use it. And I don't need really to do this since visited is in the same scope. And so I could just do V, and then I will do DFS on the neighbor, right? And so that would mean just DFS on the neighbor. And that's pretty much it. And then we can return count. So our DFS here never stops, because we should check here if you already visited something, we shouldn't go to it again. Then if we do that, we will just keep recursing. So we should check if the neighbor is not in visited. Not in visited. Then we go like this. So we have a problem somewhere, which is here. So let's just call this edge, right? And then that way we can say UV is equal to edge. Still too many values to unpack, because this is a list actually. Okay, so that's edge 0 and that's edge 1. It's not a tuple. And so here we are adding what happened. So this is E0 and E1. Okay, let's print what's in. Yeah, because the second example is not a list of lists, it's something else. Okay, cool. So it seems to be working because these assert, basically, let me just show you this one because it's an assert, so it's when it doesn't fail, that means that we have it. So let me just print it. So we can see this one is 2, and if I print for this one, the other one shows 1, which is exactly what's happening here. The first example we have 2 components. The second example we have 1 component. And basically what we did here is just construct our adjacency list, go through all the nodes. If one hasn't been visited yet, go do DFS on it and increase the count of the connected components, because that means we are starting again from another node. And then with the DFS, explore all you can reach from one node until you can no longer reach anything. And yeah, that's pretty much it, and we'll return count. And now let's try, so let's call this DFS, and let's try to code this with BFS. So let's do that here. So let's call this using BFS. Okay, and so same thing with BFS, we are going to do the exact same thing up until here. But instead of exploring with DFS, we are going to try to explore using BFS all the reachable nodes from each node that is not visited yet. And the only difference is that BFS visits level by level. Instead of going all the way deep until the end, it goes level by level. And so the only thing that will change is that we are still going to do this, except so the same thing as with DFS, except here instead of doing DFS, we are going to do BFS on I. And at the end, we are going to do the same thing. We are going to return count. And then we are going to define BFS on node V. And for BFS, we need instead to do a queue. For DFS here, I did it recursively, but I could have used the stack. That would work also. And so here with Python, we could use like a list, but I prefer to use a dequeue, because if we use a list, we'll have to pop from the first position by doing O(n) operation. That's not really good. So with dequeue, we can pop and add with an O(n) operation. And so where do we? So we start out with our queue with the value this node here. So that's V. This basically means that construct a dequeue with only V as the first as the element in it. And after that, we will just do the normal BFS, which is while q, going to do q dot pop left, so that we can get the element from the first position. And so here we would have, let's call it u. And then we are going to go through the neighbors of u. And if one of them is not visited, we are going to add it. And so we are first we need to say that u is visited. So let's add it. And then we are going to go through for neighbor in adjacency list of u. Then we are going to check if neighbor is not visited. The same thing we did for DFS. Not in visited. We are going to add it to the queue so that it gets explored next time. So I would say append, so that it adds it at the end of the queue, and we are going to append the neighbor, and at the end we are just going to do nothing basically. All we want is to mark them as visited so that they don't get visited here again, right? And that's pretty much it. So let's try. So this one also, so you can see it's calling this BFS method and does the exact same thing and works correctly the same way as DFS. There is another way to solve this problem using union find, but yeah, essentially with DFS and BFS, the template is the same. The only difference is that instead of calling DFS here, we call BFS. And yeah, that's it for now. See you next time. Bye.